Bismillah ar-Rahman ar-Rahim. Assalamu alaikum wa rahmatullah. Peace and blessings upon you all. Dear students, I don't know, we have seen the algorithmic solutions, like we saw the software solutions, Peterson's, Decker's algorithm, Lamport Bakery's algorithm. Then we saw the hardware solutions, you know, okay, uh, compare and swap. We got swapping. We saw, you know, test and set and all those things. And we saw there were a lot of problems. Like we have the first is scalability issues. We need to know how many processes we have, and the most important one is the busy waiting. We got a spin lock there, because if we one process was doing the critical section, okay, and the other process comes in, say P0 is doing the critical section and P1 comes in, if its time slice is over, for example, and it is still in a critical section, it has locked it, okay. So because we have firstly the acquired lock, and then after we do CS, we release the lock, okay. Now when P1 comes in, if P0 times out and P1 comes in, P1 tries to enter the critical section, but it's being with the P0, so it stucks with that while loop, that busy while loop, okay. And it spends all its time in this while loop, because it has to, we have to refrain it from accessing the critical section, and we did it successfully. Mutual exclusion, we are trying to mutually exclude these two processes, we did it. Or some other process also comes in, they all stuck in a while loop, and the CPU is given to them, okay. Important thing is that we have CPU with the P1 or P2 when the time slice is, say for example they got a 5 unit of time slice, they actually spend all this time slice in while loop, means doing nothing. They're basically doing nothing, they're wasting the CPU time, okay. The CPU time being wasted is a biggest problem with these algorithms, so that's why we need to fix it. Now there's other issues also, because the responsibility of implementation is with user, like in algorithmic these things, not with the, I mean, hardware solutions. In the software solutions like Peterson, Decker or Lamport Bakery, it's the user who is gonna have some this synchronization. He has to deal with it, because he has to write in a software these things. Now that's gonna be error prone, they may be having logical errors, okay. And there's a lot of overhead also, we have a lot of overhead in doing that. Now with these algorithms, if we have for example priority based, we are dealing with the priority based scheduling, and for example P1 P0 is executing CS, now P1 comes in, uh, but it has to wait, okay. Now P2 comes in, it has to wait, maybe some other process comes in, these are maybe low priority processes, okay. Now P4 comes in, which may be on a high priority base process. Now if when P0 finishes critical section, we are gonna give P4 the access, because P1 and P2 are low priority. So by that, if high priority jobs start coming in, these P1 P2 is gonna starve, okay. And there are also the deadlock issues, we take the deadlock in detail later on as a chapter, okay. And if we have on hardware solutions, now it becomes very complex, okay. For an application programmer, to do such kind of things is going to be very complex and hectic. So overall we are having lot of problems with these solutions. So that's why we got to go do something different. So this time around we take OS into confidence. I mean, we are trying to use solutions provided by the we can say OS supported solutions, okay. So we need OS supported solutions, at least to remove some of the drawbacks, and for that we have what's called as a semaphore. So the semaphore S, it is a variable, it is an integer variable, okay. It is simply a variable which you can increment and decrement, but so it's a synchronization primitive, higher level abstraction, and it was used by first time by the Dijkstra 1968 for his operating system called the, okay. So this variable is manipulated through two operations, that's important. We have two operations for that, and these are system level calls which actually does it. So because this is done by the OS itself, it's built inside the the kernel. So we have the operations which are actually the system level calls. So we have two operations. One's called P and B originally because they are Dutch. So P is also called the wait, okay, and sometimes it's also called as the down, and V, which is also called as a signal or up, okay. So we have two operations which you know can be done on the variable s, semaphore variable, okay. You can do it, these two operations, and these two operations are done atomically. Inside they may have a lot of steps, but they are done atomically, okay. We know that. So because atomically means that we can't interrupt that. If we have done P operation, it is done fully, then you can even if it's preempted, but still it is done fully. So you can't actually preempt it and do it something else, okay. Now semaphores are used because these are actually the libraries, for application programmers. These are There are the libraries, okay. And these libraries actually provide the application programmers with the semaphore, and semaphores are used by the programmers to ensure firstly the mutual exclusion, and then also it's used for other things. One of them is send signal from one process to another. Say for example, there are some classical problems we'll read later on, like the buffer problem. For example, I will tell you like this: if this is a cup, if we have two processes, one process is drinking the milk and other process is dropping the milk. Now process P2, if it want to drink the milk, firstly there should be milk, and then only P2 can drink the milk, okay. But if there is no milk, P2 shouldn't be drinking, simple as it is. So when P1 drops the milk into it, we can signal the P2 that milk is there, then P2 can drink the milk. This is what's called as a signal. That means P2 shouldn't be executing before P1, isn't it? First P1 should come, fill the milk, and only then P2 can start drinking. So if we have some scenarios where we want to defer some process, say P2, after P1, I mean P2 shouldn't be before P1. In that cases also we have what's called a signaling, and we can use the semaphores for that. And for ensuring mutual exclusion, obviously we were doing that. For mutex it's also used, okay. Now semaphore is just an integer variable, okay. Say for example s, and you can assign it to some, initialize it to some non-negative value. Maybe I initialize it to 1. Later on we'll see the binary versus counting semaphores, where you can assign the maybe 10 or something, more than 1, okay. Then a process can decrement the semaphore if its value is positive. If its value is positive, say for example it's 1, okay. If its value is 0, say for example some process comes in and its value becomes, it decrements it and it becomes 0. Now s is 0, that means it's blocked. The process blocks, gets into the queue, and we say that it's sleeping. What I'm saying is, for example, we have semaphore also used for resources. If we have, say for example, one resource, and say we have a printer, okay, and P0 is accessing printer. So what it does, it has the s equals to 1 firstly, and P0 comes in. It decrements the s. If it is positive, it is positive. So what it does, it makes it 0, okay. That means it locks it, and now it starts accessing the printer. Now P1 comes in. It sees first the s, and it sees that, oh, s is already 0, so you can't decrement it. So what it does, it goes on sleeping. That's the main difference between the other algorithms and this one. In other algorithms, the P1 and P0. Now P0 is accessing the critical section. How? Because s was initially 1, it decremented it to make it 0. Now P1 comes in, it sees, oh, s is 0, so it can't decrement it. So what it does, it is not in a busy while loop, rather it goes and sleeps in a queue. So we have a queue, and P1 goes here and sleeps. What does it mean? Sleeps means is CPU will never be given to it, okay. So when P1 comes in, it sees it's locked, semaphore is locked. So what it does is, how it sees it is locked when s is 0, okay. So it goes on and sleeps. So sleep means it's not in a ready queue, So it is in a waiting queue or blocked queue, whatever it is, and it is the job of then the P0 to actually wake him up. Okay, so by this we that busy wait loop stuff is gone, because P1 will never be given now the CPU, because we know if we give the P1 CPU, it's gonna stuck in here. It's gonna do nothing, because it wanna do critical section, which is being done by P0. So better P1 sleeps. So that means the scheduler is not gonna assign P1 the values. Maybe it will give some other process, say P3 or P2. If P2 also wanna access this, P2 will be also in a sleep queue now, because P0 is accessing critical section. Now for example, P3 is something which has to do something else. Now if P0's time slice is over, processor will be given to P3. Now P3 will be doing its own stuff, because it has nothing to do with the critical section which P0 is doing. So P3 can go, P3 can run. So it's not wasting the CPU time now with P1 or P2, because if we would have given, like in our previous algorithms, the time slice to be given to P1 and P2, they are gonna do nothing, because they have to be mutually excluded here, right? So mutual exclusion is there, so they would only waste the CPU time. Now in this Semaphore implementation, this P1 and P2 goes into the separate queue, okay, where they sleep. What does that mean is the scheduler will not assign CPU when P0's time slice is over. It rather gives to some other process which has which is not having a contention with the CS. Okay, it has to do some separate job, so let it do. So CPU is not wasted. CPU time cycles are not wasted with P1 and P2. This is the most important thing. So that's why we say that if it is the positive value, we will make it decrement it. Okay, but if it is 0, that means we can't have we can't access that critical section or that resource something. So we are the process blocked. Okay, so we put in the queue and we say it's sleeping on the semaphore. So this is your down operation, okay, or wait operation, okay, or P operation. Okay, now increment when you are done, when P0 is done, common sense is it's got to increment the S to back to 1, because if it's done with the CS, okay, what it should do, it should increment S is equal to S plus 1, so that other processes, if they come in, they see that it is S plus 1. It not only increments it, but also it has to actually it has to wake up some process. Okay, so before incrementing, it actually wakes up some process. If there is some sleeping, some process sleeping, it has to wake up. Okay, wake that up, and then that process actually will increment that. We'll see this in a short while. So I'm saying if value is 0 and some process sleeping on the semaphore, so we got to unblock the 1. Okay, otherwise the value is incremented. Okay, so we not incremented straight away actually, because if we increment it, that means other process will come on. These are sleeping, say P1, P2. Now P4 comes in, and if we increment it directly, it will test the S, and it sees it is 1, so it will start doing. So these sleeping guys will sleep forever. So rather, before we actually increment it, we actually see first here that if some process is sleeping, we wake it up without incrementing the S. So S is remains 0, and P1 can access critical section, and P1 then sees, oh, P2 is sleeping on the semaphore. It wakes it up, and when there is no process waiting here, no process sleeping here, then we go for S is equal to S plus 1. We release the lock. Okay, this is how we operate in the semaphores. So in general, if we have to do critical section, we do firstly the wait operation on the semaphore S, and you can also call it as a down operation, or you call it as a P operation, whatever you like to call them. I call it wait, and we call it as a signal. And after critical section, you have to do signal on the S. Okay, and some processes call it down. Some, literature, you see the books, there is the down written, or up, that's the same thing. Or we have a P and V operation. You do critical section, after that you do V operation. So I will use this notation now on wait and signal. This is same as prober and verhogen, or down and up, whatever you like to call it, but I will now adapt this notations. Now let's try and see this wait and signal operation. This is the wait operation S. So firstly, they are atomic. We should understand that they are done in fully, they are not preemptible, and so on. We know that. So we see simply if s is greater than 0, I mean if s is positive, okay, what we do is we will gonna do s is equal to s minus 1, we're gonna decrement it, okay, and we return back. Now there it has two parts. If s is positive, then we gonna decrement it. That is, in other words, we lock it. Okay, say s was 1. Okay, and what we're gonna do is we decrement it and make it 0. That means it's locked. S0 will uh, tell other processes that it is locked. Now maybe some process has done it already, and a process comes in, does wait on the s, but it's already 0. So if s is not positive, okay, if s is not positive, okay, so then what are you gonna do in that case? We actually put that process into the sleep queue. Okay, put that process. If s is not positive, if s is positive, that means nobody is accessing the critical section, or nobody is using that resource, or whatever it is free, we can access it. But first we should lock it. How we lock it? We decrement the s, make it 0. Now if s is not positive, that means already somebody has actually worked on the s. That means we should sleep, or we block that process, okay, and it goes in a sleeping queue. So put that process into the sleeping queue, okay, and it will only wake up if by some other process which does the signal on that process, okay, and wakes it up. Do you understand? So this is our wait operation. So we have technically speaking 2 points in it. One, if s is positive, then make it decrement it and access the critical section. You can go ahead and access the critical section, you are not blocked. But if s is not positive, you will be blocked, you will be kept in a sleeping queue. Okay, so you're gonna sleep here. Now then there is a signal, okay, operation on that s. So it's also atomic, okay, and what it gonna do is it will first see if there's somebody is sleeping, okay. If there is one or more processes sleeping on that semaphore s, then you're gonna select one process and wake it up, okay. So if I say like this, if some process is sleeping on semaphore s, then wake it up, okay. You gotta you know that process is going to be selected and waken up, okay, and return. Then you return, okay, you can return it here. Similarly, like this, it has also the second part. Maybe there is no process sleeping. Maybe it was the last process who does the signal, okay. So maybe there is no process sleeping. So what are you going to do? You will increment s is equal to s plus 1, so that you release the lock, okay. So technically you are releasing lock here. So in a wait, we see if s is semaphore is greater than 0, that means it's positive, so decrement it and access the critical section. But if it is not, you are blocked, the process is blocked and put in a sleeping queue. And a signal before releasing the lock, see if somebody else is sleeping, so wake it up in a first come first order, right. So wake that process whosoever has come and sleeping. Say for example p0 come, then p1 has come, then p2 has come. It will wake firstly p0, okay, it will not release the lock, it will wake the p0 and return here, okay, return back. And then when p0 is done, it will tell the signal, it will wake the p1. Then p1 when finish its critical section, then it does the signal operation, and then p2 wakes the p2. And when p2 comes in, does this finishes critical section, okay, it will see that nobody is sleeping then, because queue will be empty. Then what it does is it will increment. In that case, it will not do this thing, it will do this thing, okay. It will increment the s and return, and then return, okay. So that means it releases the lock. Does it make sense? Now semaphores can be the binary semaphore or the counting semaphore. For example, you have a critical section, the mutual exclusion problem, and there are n processes. So many processes, whosoever they are, say p0 up to pn, okay. In that case, we make a semaphore variable, a shared variable, which can be shared by all these processes, okay, and we can put its value as 1, or it can be 0 or 1 only, right. If some process comes in, it does the wait operation on the s and makes it 0, and other processes will all see that s is 0 and they all go into the sleeping queue. and later on we can do the signal operation. The signal operation wakes the process from the sleeping queue, and if there is no waiting process, then make it back to the zero. Okay, so this is the mutual exclusion problem. But sometimes we have the problems like we have resources. Say for example we have three printers. What do you say about that? If you have three printers, now you can't make S1, and we have P0 up to Pn, we can make S this time 3. Okay, now P0 comes in, does the weight operation on the S. What a weight operation does, it makes it S is equal to S minus 1. If it is positive, make it 1 lesser, so P0 will make it S2. Okay, now P1 comes in, because we have three printers, so P0 has accessing one printer. Whatever we have two more printers, right? So P0 is accessing one printer, we have still two printers left. So if P2 comes in, we should not block that because it can access the second printer. So what it does is it decrements it does weight on S, and it sees it is positive, so it makes it S is equal to S minus 1, that is the 1. So it is not a negative, so it's not 0, so it can access the printer. And P3 comes in, it again sees we have one more printer, so we should assign it. So P3 does the weight on S, and it makes it 0 and access the printer. Now if P4 comes in, it sees that S is 0, so it should be in a sleeping queue now. Okay, P4 should be in a sleeping queue now. Rather than decrementing S, it goes to the sleep. It's blocked, right? So because we have three printers, similarly we could have, maybe we have 10 printers, so S will be 10, or some, not only printers, some other resources if we have. So we can actually assign S equivalent to that resources. When they are done, after that it will hit 0 and the other process will be blocked. Okay, does it make sense? So that's why we have a counting semaphore where value range from 0 to n, okay, where n can be any integer number. It depends upon what kind of resources you have, how many resources you have, and so on.